Okay, so we'll go ahead and start now. So good evening, everyone. Good morning, some of you. It's my huge pleasure to welcome Nima Nari for this talk. Nima did his BSc from Sharif University in Tehran and since then has been in the Bay Area. His PhD was at UC Berkeley, then he did a postdoc and a research engineer stint at Stanford University, intermingled with a couple of stints at the Simons Institute of Research, Simon Institute as a research fellow in Berkeley. He's currently an assistant professor in the computer science theory group at Stanford University. His research interests include geometry of polynomials in algorithmic applications, approximate sampling and counting, spectral graph theory and spectral algorithms, algorithmic game theory and mechanism design, and today's talk on fractionally log-concave and sector stable polynomials combines many of his interests. He's a delightful speaker, and we are, you know, very much looking forward to his talk. So, Nima, the screen is yours.
All right. Thank you so much for the introduction and having me talk here. So this is a joint work with students at Stanford, Yagana, Kiran, and June. So let me begin the talk by posing a motivating question behind all of this. And that's a question about counting matchings. So imagine you're given a graph and the question you're given is to just output the number of perfect matchings in this graph. So this question is very fundamental. It was shown to be one of the major Sharpe completeness results that was first shown for a P problem. This work was by Valiant. So Sharpe complete just means that probably there is no efficient algorithm that can output this number efficiently in polynomial time and exactly. Okay. So once there is basically very little hope of exact counting of the number of perfect matchings by an efficient algorithm, the next best thing that you can hope for is to approximately count this. And there is in the counting and sampling literature, there is a very well-defined notion of what approximation means. And that's the notion of FP-RAS. So the goal here is to basically output a number that is within some relative error of the count, and that relative error can be also controlled by the algorithm. So for any epsilon parameter that you want, the algorithm would be able to output a 1 plus epsilon approximation with high probability. So for example, for now, think of the epsilon as like 10%. So you want 10% relative error. Okay. For a lot of problems, including this one, it doesn't matter basically what you set as your error parameter. Anything reasonable can be boosted to any other epsilon you want. Okay. So unfortunately, for this question, we don't know whether approximation is possible or not. So the question is still open. There is evidence that maybe algorithms that people had hoped for wouldn't work, but there is nothing very concrete about either direction of this question. So one of the important aspects of this question is there is this general meta question of in general, if you want to be able to approximately count the number of some combinatorial structure like perfect matchings, you better at least be able to distinguish the case where the number is 0 or not, right? Because if your approximation is multiplicative, you are already distinguishing that number, right? So problems for which you can distinguish 0 versus non-zero, those are problems you can solve in P. So there is this meta question of for which of those P problems can we actually get a better algorithm that doesn't just distinguish 0 from non-zero, but also gives you an approximate count as well. So this is one of the major open cases of this meta question. So even though we don't know whether perfect matchings in all graphs can be approximately counted or not, there are two major classes for which we have good algorithms that can count. There is the class of bipartite graphs and planar graphs. So bipartite graphs, it was shown in a major work by Jerome Sinclair and Vigoda that you can actually get an FP-RES for it. So for any parameter epsilon, you can count the number of perfect matchings in a bipartite graph within a factor of 1 plus epsilon. And this was based on the Markov chain Monte Carlo method that was initially suggested by Broder for this problem, then developed by Jerome Sinclair, and finally made to work for perfect matchings in bipartite graphs by Jerome Sinclair and Vigoda. So there is another major class, planar graphs. And this class is a little bit different from bipartite graphs because on planar graphs, you can actually exactly count instead of just approximately. Okay, so there is a polynomial time algorithm that can count the number of perfect matchings exactly, no approximation. And this was shown by Castellane first in 67. The motivation for counting perfect matchings here came from a model studied in statistical mechanics called the Monomer-Dimer system that I'll talk about later in the talk. I won't go too much into the details of what this algorithm is, but at a very high level, the idea behind this is you basically come up with a signing of the adjacency matrix of the planar graph so that the determinant of that signed adjacency matrix gives you the number of perfect matching squared. And basically Castellane, following earlier work by himself and Temperley and Fisher, showed that you can always construct these signings for planar graphs. So the talk today is actually kind of a happy marriage between these two types of algorithms, Markov chain Monte Carlo, and these algorithms on the right that count perfect matchings via determinants. I saw that
Nima, Devdat had a question for you. So exact counting in bipartite graphs is NP hard. Is that right?
Yes. In fact, this earlier result by Valiant showed this for bipartite graphs.
Okay.
Yes. Okay. Yeah. So the bipartite case is actually a very important case because the number of perfect matchings in bipartite graphs is related to this quantity called the permanent of a matrix, which is of interest in many places. And yeah. Okay. So all right. So now let me pose a slightly modified question. Suppose that instead of counting perfect matchings, you wanted to count matchings of a particular size k. So k is also input to the algorithm, and you want to count the number of subsets of edges of k edges, which are a matching. Basically, no two edges are adjacent. So so this slightly modified problem, which is actually a generalization because you can also set k to be n over 2. So this slightly modified problem is not harder than just counting perfect matchings in general. That's because given a graph, you can basically add a bunch of dummy nodes and connect those dummy nodes to the rest of the graph in this fashion. And by controlling the number of dummy nodes, you control, so any perfect matching in this new modified graph corresponds to basically a matching of a particular size on the original graph. If you just consider the edges of the perfect matching that are inside, those would give you a k matching. And by controlling the dummy nodes, you can basically account for the number k. So it's just enough to count perfect matchings in this graph. And this strategy naturally extends to the bipartite case too. So you can just use the algorithm of Jerome Sinclair and Vigoda to count k matchings in those graphs. But it somehow, I mean, it fails for planar graphs. So these dummy nodes that you add, they have to be connected to everything else in the graph, almost everything else at least. And therefore, they have to have a lot of intersecting edges. So the graph doesn't remain planar. So, okay, so this is a heuristic argument for why this doesn't work, but there is actually a more fundamental reason why this doesn't work. So Jerome showed that even though you can count perfect matchings in planar graphs exactly using a polynomial time algorithm, if you consider this modified problem of counting k matchings, then the problem is sharply hard. So again, there is very little hope of designing efficient algorithms here. Okay, and so the main result I want to highlight today is that for this problem, which is now sharply hard, we have the next best thing, which is approximate counting within any desired factor. Okay. So before going into the details of the algorithm, I just want to highlight something. We actually don't use planarity that much. The only thing about planarity that we use is that in the class of linear graphs, we can count perfect matches. So this theorem naturally extends to any other class, any other downward closed class of graphs, where you can still count perfect matchings, and there are some beyond planar graphs. There is the class of bounded genus graphs. There are some minor free classes of graphs where you can still lose. Okay. Yeah, so more generally, we can also deal with weighted counting of matchings. And let me describe what that is. So that's often known as the Monomer-Dimer system. So a Monomer-Dimer system is basically a weighted distribution on the set of matchings of a graph. The way this weighting is defined is you have a weight for every vertex, that's called the monomer weight, and a weight for every edge, that's called the dimer weight. And a monomer-dimer configuration is just a matching, so a set of edges that are not adjacent to each other. And the weight of that particular matching would be the product of the edge weights that are in the matching times the product of the vertices that are not matched by the matching. Okay, so the vertices that are outside of the matching are called the monomers. These are called the dimers. And you can think of this as like particles that are forming bonds with each other. So the things that get bonded are called dimers. Things that don't get bonded are called monomers. Okay, so the natural extension of, so for perfect matching, this is defined to be pro. What does pro mean?
Sorry, I meant zero. So if it's a perfect matching, then there is no vertex not matched. So what do you define?
Yes. So basically, if you set all of these ZVs to 0, then you get a distribution on perfect matchings. And then you can actually exactly count that using the algorithm of Castelli. Okay. So now the question about, so this is a weight, and then you can normalize this to a distribution, to a probability distribution by just dividing by the sum of these weights. And the natural equivalent of counting perfect matchings here would be just computing the partition function of this distribution or the sum of these weights, overall matchings. Okay. So because of some very powerful results coming from work of Jerome, Valiant, and Nazirani, approximately sampling from this type of distribution and approximately counting or approximately computing the partition function are algorithmically equivalent. So if you can produce samples that are, let's say, epsilon close in total variation distance from this distribution, then you can also approximately count and vice versa. So what I'll show you for the rest of the talk is how to produce samples from this distribution. Okay. So even for this model, even if you don't restrict the size of the matchings to a particular number k, then in general, counting is still sharply hard. So unless you let's say restrict the monomer weights to be 0. But in general, the counting problem is still sharply hard. And this was again shown by Jerome. There is one particular restriction that you can put on the weights, which makes this tractable using earlier work. So Jerome and Sinclair, who were basically building the Markov chain Monte Carlo method on their way to perfect matchings for bipartite graphs, also showed that in this case, in this monomer-dimer system, as long as the weights are polynomially bounded, let's say you don't have monomer weights, and let's say the dimer weights are polynomially bounded, then there are efficient Markov chain Monte Carlo methods that can sample from this distribution for you. So counting with weights is just computing the sum of these weights. So the sum of these weights overall matching them. Yes. Yes. Okay. So our algorithm basically works even in the monomer-dimer case, even if you want to restrict the size of the matching. And the important differentiating factor here from earlier work of Jerome and Sinclair is that it works for all weights, not just polynomially bounded weights. All right. Okay. So so to describe the algorithm, I want to mention first that it's actually based on a framework that I developed with my co-authors earlier work called Spectral Independence, and this framework is based on the analysis of high-dimensional expanders. So so the main point in this framework is analyzing the correlations in your distribution. And you know, it's been known for a very long time that correlations in a distribution are somehow maybe connected to whether or not basically efficient sampling and efficient counting is possible or not. So there are many cases of this in the counting and sampling literature. So let me point out some. So there are some distributions on combinatorial structures that satisfy something called negative correlation and many generalizations of it. So the classical example of this is the distribution of spanning trees in a graph. So given a graph, if you sample a uniformly random spanning tree, it satisfies what's known as negative correlations. And what that means is that if you fix any two edges, E and F, that are different, once you condition on F, the probability, sorry. Okay, so once you condition on F, the probability of E actually goes down. So you know, any two edges are satisfy this, and that's called negative correlations. And Federer and Mihai basically were the first people to basically use this type of property to design efficient sampling and counting algorithms. So there is another very famous property called decay of correlations. It's actually a class of properties under this umbrella term. But you know, they're all various strengthenings of this fact that let's say you have a model on a graph. The famous example of this is the hardcore model, which was first studied by Weitz. But let's say you have a model and a graph. So for example, the hardcore model would be a distribution on independent sets, subsets of vertices of a graph. So in some regimes of the parameters of this hardcore model, you have this property called decay of correlation, which in the simplified form says that if you look at two things that are far apart in your graph, let's say you look at two vertices that are far apart, U and V, then those two vertices are almost independent of each other, meaning that the probability of U, let's say being in the independent set given V, minus the probability of U is very tiny. And this difference goes to 0 as the distance goes to infinity, as the distance basically gets larger. Okay. So there is another class of properties that I'm going to call spectral negativity. So this is a property that I won't define on this slide, but maybe later. But I'll give you the example of it. So let's say you have a set of vectors in some vector space, and you want to choose a basis formed from these vectors uniformly at random. This is what's known as a matroid, so a distribution of this kind basically it was at some point believed to actually satisfy the earlier negative correlation property, but then it was shown that it doesn't in general. But it satisfies something called spectral negativity. So basically a matrix that you can form from the correlations of pairs of things in your distribution ends up being negative semi-definite. But I'll show you what this means later on. So we have these types of properties, and the natural question you might ask about monomer-dimer systems is whether monomer-dimer systems satisfy any of these. And I want to show you that basically they don't satisfy the first and the second, and they don't satisfy the third, but they satisfy basically a weakening of the third. All right. So why don't they special classes of matroids satisfy negative? Yes. So there is a special class of matroids called balanced matroids that satisfy negative correlation, but the definition of that class is the class of matroids which satisfy negative correlation, a strengthening of actually negative correlation. Yeah. So I mean, more concretely, the only class, or the only famous class of matroids that is known to always satisfy negative correlations is the class of regular matroids. But there are some other, kind of niche classes of matroids that also do that. But in general, if you take, let's say, a linear matroid like this, it won't satisfy negative correlation. All right. Okay. So correlations in monomer-dimer systems are not of any of the types that I showed you, and let me demonstrate that via some examples. So let's a monomer-dimer system, it's a distribution on matchings, but you can also just pay attention to the vertices that get matched or the vertices that don't get matched. That's like a subset of the vertices of the graph. So even that subset doesn't satisfy some of these properties that I mentioned, okay? Let alone just a subset of edges. For example, the correlations in the set of monomers in a monomer-dimer system can be positive. And here's a simple example. Just take a graph with just one edge, and let's say all of the weights are 1. Now the two endpoints of this edge are perfectly positively correlated. They're either both in monomer or neither of them are. Okay. So you can also have long-range correlations between things in this model. So a quick example of that is, let's assume that you have a path of correct parity. It should be, I think, I don't know, odd or even, depending on whether you count edges or vertices. And let's say that the edge weights are all 1, the dimer weights are all 1, but the monomer weights are set according to this picture. So all of the middle ones are set to 0, the endpoints are set to 1. Okay. So it's not hard to see that the monomer-dimer system here is just supported on 2 matchings. One is basically the odd edges and one on the even edges. Okay, and so whether or not this vertex was a monomer would perfectly tell you whether or not this vertex was a monomer. Okay, exactly one of them is a monomer at any given time. So because you can make this path arbitrarily long, you don't have, in general, decay of correlations, right? There are things that are very far apart but are perfectly correlated. So I should mention that there is a very important asterisk here. In the case of, let's say, unweighted graphs, or more generally polynomially weighted graphs, you can show that not only do you have a decay of correlation between vertices, but you also have decay of correlation between edges as well. So this was shown by Beati, Gomarnik, Katz, Nair, and Titali. Right. Okay, so the type of thing that we show for the monomer-dimer system holds is this other property, which is maybe a little bit, it's actually not very comparable to these other properties. So what we show is that if you fix any vertex like this blue one, the number of, this is like the informal version, I'll give you the formal version later. The number of other vertices that are highly correlated with it is not too many. Think of it as like being bounded by a constant. Okay. So this goes well with this case, because here the example I constructed, I was able to correlate this vertex with this vertex, But if you think about it, this vertex is independent of the vertices in the middle, because the vertices in the middle are always part of the, are always not a monomer. They're deterministically not a monomer. So for this vertex, there is only one other vertex that's perfectly correlated with it. And basically that's what we show in general holes. Okay. So, all right. So now I want to give you a high-level overview of this spectral independence approach that I've been mentioning. So the high-level basically recipe here is if you want to sample from a combinatorial distribution, like I mentioned, you first have to do some transformation to make it a distribution on basically the hyper edges of a hypergraph. So think of it as a distribution on size k sets out of a set of n elements. Okay. So once you do this transformation, there is this basically well-studied notion. There are a couple of notions, but there is one that's useful for spectral independence. I'll get to it. But there are these well-studied notions of high-dimensional expansion. These are generalizations of the notion of like expander graphs to hypergraphs. And the goal here is to show that these notions hold for your distribution when you view it as a weighted hypergraph. And then once you show this, then you get automatic sampling algorithms. There are these natural random walks that people have studied in the context of high-dimensional expanders. And as long as you have high-dimensional expansion, they mix fast. Okay. So this recipe has been successful for a bunch of different distributions, but maybe in the interest of time, I'll just skip these. Okay. All right. So let me demonstrate this for the matroid example that I mentioned earlier, and then we'll get back to Monomer-Dimer systems. So you know, you have to first convert whatever distribution you have to a distribution on a hypergraph of size with hyperedges of size k, a k uniform hypergraph, basically a distribution on size k sets out of a ground set of n elements. Okay. So some distributions are naturally of this type. Some distributions you have to do a little bit of work to make them of this type. For example, matroids are always of this type. You know, if you are in k-dimensional space, then the subsets of vectors that form a basis are always of size k. So naturally, you have a distribution of this type. So this mu would give a weight of basically 1 to things that are inside that are a basis, and a weight of 0 to anything that's not a basis. Okay. So once you have a distribution like this, there is a natural random walk that you can study. It's basically a generalization of the very famous Glover dynamics. So this random walk basically transitions between these size k sets, which are the support of your distribution, and size k minus 1 sets. Okay, and the way it works is you start from some size k set, like this one on the left, and then you drop one of the elements in the size k set uniformly at random. So that takes you to, I don't know, one of these 3 places. You do this part uniformly at random. And then once you are at one of these k minus 1 size sets, you go back up by adding another element. This time you do it with probability proportional to the weight of the resulting set, or the or whatever your distribution tells you, basically. Okay. So each step of this random walk is basically the combination of these 2 steps, 1 and 2. And if you basically continue doing this, you might hope that you would converge to your distribution mu. Actually, you can easily show that this type of random walk always has the distribution mu as its stationary distribution. So under some mild ergodicity assumptions, it would converge to mu. But the question is, how fast is this convergence? Okay. And high dimensional expansion is a way of basically quantifying this convergence and showing that it's Pauli bound.
Nima, one question for you. The
Yes.
step one, can it be made similar to step two, rather than doing uniformly at random, to be proportional to?
Perfect. Yes. So yes, the question is basically instead of uniformly at random, maybe you want to drop elements with some given weights p1 up to pn, maybe, right? So yes, there is a natural generalization of this where you come up with some p1 up to pn, you drop according to those, and then you have to modify this step to make mu the stationary distribution. So this is I guess this is the natural thing to study, but that more complicated version, actually I've studied this in a paper with Mikhail Jarozinski. So it's actually useful. We haven't been able to show that this particular random walk is useful yet. A generalization of it we've shown to be useful, but I guess let's not get into too many details of that. But the point is that random walk can sometimes mix much faster than this. So if let's say k is much larger than n, let's say, then that random walk can somehow be made to work much faster in the case that you can come up with a good p1 up to pn. We can discuss this more offline, I guess. All right. So okay. So for the monomer-dimer system, the distribution is actually not in the standard form. If you haven't restricted, let's say, the size of the matching to be k. Okay. Let's say we are in the general monomer-dimer system with no restriction on size. There is a natural trick that you can do to make this of this standard form of a distribution over k uniform hypergraph. Okay, so for now, let's say that I'm only looking at the monomers in the monomer-dimer system. So that's a distribution on vertices, subsets of vertices of the graph, but this subset can be of varying sizes. But here is a trick that you can do to make this of a uniform size. Basically, for each vertex in the graph, introduce two elements. Let's say a gray element and an orange element. So overall, you have twice as many nodes as you have as your n. And a configuration, basically an assignment of monomer or not monomer to the vertices, would just be a subset of these n elements, and the size of this subset would be just the number of nodes. For each node, you select one of the two. So an assignment or a configuration would just be a subset of size k out of these n elements. Okay. And once you view your distribution like this, then the random walk that I mentioned is the famous Glover dynamics. So here, size k minus 1 sets are configurations that are missing a vertex. So I'm showing that by white vertex here. And the random walk basically does this. It starts with a configuration of the monomers. It drops one of the vertices chosen uniformly at random. And then once you've dropped it, you get to a size k minus 1 set. You choose one of the two possible values for it back using the weight of the resulting configuration. Okay. So the only thing we use actually about planar graphs is that once you look at just the monomers, you can compute the weight of each monomer set. Yeah, so that's the only part where we use planarity. The rest of the talk actually works for all graphs. No need to assume planarity. So just to be clear again, so here what I mean is once you fix the set of monomers, let's say you fix the monomers to be these two vertices. Now the weight of this monomer would be just the number of, or the number of perfect matchings on the complement, basically. Okay, and because the complement is still a planar graph, you can use Castellan's algorithm to count the number of perfect matchings in that part. That would be the weight of this monomer set. Okay. All right. So one quick thing that you might have noticed about this random walk for Monomer-Dimer systems is that there is an issue with running this as stated for Monomer-Dimer systems, and that's a parity issue. So the problem is once you basically unmark a vertex here, so let's say you unmark this vertex, you go from here to here, let's say, you have to go back to the same place that you started from, because the number of monomers in a monomer-dimer system always follows the same parity, odd or even, based on the parity of the total number of nodes. Okay? So you can't, so for basically this vertex, there's only like one choice that you can make. So you're not making any progress by continuing this random walk. So fortunately, this is actually a very easy problem to fix. Instead of dropping one vertex at a time, you can just drop two vertices at a time. Or more generally, in the case of weighted hypergraphs, you can walk between size k sets and size k minus 2 sets, let's say. And here is a pictorial view of how this works. You just drop two vertices, and then you recolor them back up according to the weight of the resulting distribution, the resulting configuration. Okay, so all right, so there's actually nothing stopping you from going beyond k minus 2. So you can do a random walk between k and k minus 3, k and k minus 4, all the way to even, let's say, k and 0. So a random walk between k and 0 sets would just drop all of the vertices and then color them back up according to the weight of the resulting configuration. So it mixes in just one step. Oh, sorry, there is a question that I missed. Yes. Yeah. So everything is done up to everything in this random walk was basically proportional to the weight of the resulting configuration. So if you know it up to a constant of proportionality, you can still run this. Yes, thanks for a good question. Okay, so the random walk between k sets and 0 sets, it actually mixes in just one step, but of course it's not algorithmically implementable, because you have to consider all possible configurations when you're going back up from the 0 set to k set. There are exponentially many of those. So even though this is not algorithmically useful, it still turns out to be useful for the analysis. Not this random walk, because this is very trivial, but the slightly less extreme version of this random walk. So if you move between sets of size k and sets of size 1, then this gives you a random walk that's useful to know analytically, although it's still not algorithmically implementable by itself. So here is how this random walk works. You drop everything except one vertex, and then you move back up, right? So it's basically like a random walk between your distribution and just the ground set of n elements, okay? And the reason this random walk is useful analytically is because it's somehow related to the correlations in your distribution. And the way to see this is, I've been talking about a random walk that moves from k sets to basically 1 sets and then back up to k sets. But you can flip these two steps. So instead, you can move from 1 set first to a k set and then go back down to a 1 set. These two random walks, they are actually very related to each other. So the probability transition matrix for one of them is like the matrix AB, the other one is like BA. So their spectrums are basically almost the same, except for a bunch of 0 eigenvalues, for example. So in order to study basically the random walk between k and 1 sets, you might as well just flip this and study the flip random walk between 1 sets and 1 sets. And that's described by just an n by n matrix of probability transitions, right? And this matrix, the entries that show up in it are just the conditional marginals of the distribution. Basically, the probability of transitioning from I to j is just the conditional probability of j being inside a sample of your distribution, given that I is in that sample. And the whole thing you have to divide by k. The reason for this 1 over k is because when you go down, there's a 1 over k chance of choosing that particular element. Okay. So in order to, let's say, study mixing properties of this, you can study, let's say, the spectrum of this matrix. Okay. So the question is, how fast does this k-to-1 random walk mix? And as I said, you can just study the spectrum of it to analyze this mixing, or you can even to basically make things a little bit more easy. You can even kill off the top eigenvector of this matrix. So for any probability transition matrix, the top eigenvector gives you an eigenvalue of 1. So if you kill that, now the top eigenvalue gives you basically the important parameter for mixing. So here I've done that. If you just subtract the stationary distribution from each row of this probability transition matrix, you kill off the top eigenvector. And now the question is, what is the top eigenvalue of the remaining matrix? Okay. So let's even ignore that factor of 1 over k that was present. So without that vector of 1 over k, let's call whatever matrix we end up with the correlation matrix. And the reason for this naming is the entries of this are somehow measuring the correlation between various elements in your distribution, right? So the probability of j given I minus the probability of j itself, right? So for example, if you have decay of correlations, a lot of entries of this matrix would be 0 or near 0. Okay. All right, so now basically in high dimensional expanders, the thing that you have to show is that basically this matrix has bounded eigenvalues. And more specifically in the spectral independence framework, what you have to show is that this correlation matrix has eigenvalues bounded by a constant. Okay. So this is much stronger than just the mixing of the random walk between k sets and 1 sets. For mixing of that random walk, you just want these eigenvalues to be bounded by constant smaller than 1 times k. That's because you already divide by 1 over k. So as long as the eigenvalue ends up being smaller than 1, then you mix fast. But here I'm saying the eigenvalues without that factor of 1 over k are bounded by 1. This is a much stronger assumption.
There's a question whether this follows from Perron-Frobenius when the correlations are negative.
Yes. So when correlations are negative, you can actually show that the sum of basically the rows of this matrix, the L1 norm of each row of this matrix would be bounded by a constant, and that follows that basically implies this.
Also, so there seems to be some kind of a bar on the slide saying this play button and a line.
Okay. Sorry. Oh, did it go away?
Yeah, it's gone now. Thanks.
Okay, sorry.
I just came from last
see that. Okay, sorry. Okay. Yeah. So the promise of the spectral independence approach is that if you can show that this correlation matrix has eigenvalues bounded by constant, not just for your distribution mu, but also for its conditionings. And by conditionings, I mean once you let's say you condition on your set containing a set of particular elements. So if you show this for your distribution and its conditionings, then the promise is that the efficiently implementable cousins of this random walk, the ones that drop constant many elements and then go back up to k. So those ones would actually mix in time k to the order of 1. And all of these orders of 1 are actually related. So basically the worse your bound for lambda max is here, the larger the number of elements that you have to drop, and the worse this basically relaxation time would be. Okay, but as long as things are constant, here everything remains a constant. You can just basically run this for polynomial many steps. All right. So this bound on the eigenvalues of the correlation matrix, you can also restate it in terms of a different quantity. And I'm just, this slide is not very important except for the introduction of this polynomial. So given your distribution on size k sets of a ground set of n elements, you can define a polynomial that's like the partition function of your distribution, except you view some of the weights as variables in it. So in the case of monomer-dimer systems, basically you assign a variable zi for each vertex, and then you sum over all sets in your distribution, the weight of that subset times the product of the variables corresponding to the elements of that subset. So this is a polynomial that you can call the generating polynomial over distribution. It's like a partition function with just these viewed as variables, and having an eigenvalue bound in the correlation matrix basically translates to this language in terms of this polynomial. So think of your polynomial G and then replace the variables by some fractional power of them. So think of like square root Z1, square root Z2, and so on, and then take a log of the resulting thing and see whether or not you get a concave function over the positive orthant. So as long as you can do this for some fractional power alpha that's like, at least a constant, let's say, I don't know, if alpha equals a half or alpha equals a quarter or something, then you get basically the fact that the correlation matrix has eigenvalues bounded by a constant and vice versa. Okay. And you actually need to show this just around the point z equals 1. But for the monomer-dimer system, basically, we can show that this holds for all z in the positive orthant, not just z equals 1. And one point about being log-concave at all points in the positive orthant is that you get conditionings automatically. If you remember, I mentioned that you have to show that the correlation matrix is bounded not just for the distribution, but also its conditionings. And conditionings, basically, you can get them from these weights. And the very high level overview of that is if you want to condition, let's say, your distribution on the element 1 being inside your set, you just put a very large weight in front of Z1. That gives you basically a new distribution and as long as this lambda is very large, that's like conditioning on element 1 being inside your set. And this type of operation preserves, a concavity of the type I mentioned. Okay, so now the strategy we have for bounding the spectral norm here is for the spectral norm of the correlation matrix here is by bounding the L1 norm of the rows of the correlation matrix. So this is the more precise version of the property I showed you earlier. Basically, for any blue vertex V, we show that the number of for any blue vertex U, we show that the number of other vertices V that are highly correlated with it is bounded in the sense that the sum of all of these correlation measures is bounded by a constant. Okay. And if you show that the L1 norm of rows of a matrix are all bounded by by constant, then you get automatically that the maximum eigenvalue is bounded by that constant as well. Okay. So this strategy actually has been used for a lot of other distributions, including for example, in the case of negative correlations, this works. You can show that the L1 norm of rows would be bounded by a constant. But it's been shown in the case of many other distributions that have decay of correlations. So as I showed you earlier, monomer-dimer systems don't generally have decay of correlations. So instead, the property that we rely on to prove this is the location of roots of that polynomial that I introduced in the previous slide. So formally, this is the property of that polynomial that we use. The property is called sector stability. Is it fine if I go a few minutes over, or should I try to wrap up?
I think it's fine. Okay.
All right. Sounds good. So the property is called sector stability. And sector stability means that for this polynomial, if you choose variables from inside of a sector in the complex plane like this, so think of an infinite sector symmetric around the positive real axis. You want your polynomial to have this property that whenever z1 up to zn are chosen from this sector, you don't get a value of 0. Okay, And this is somewhat related to these other properties studied in statistical mechanics originally, where not having zeros where z1 up to zn are near the real axis is known as not having basically phase transitions. Okay, so this is basically so we are basically using that type of property to show some algorithmically positive result. Yes, so there is a question whether real stability is a special case of this, and it is when you have a homogeneous polynomial. So when you have a homogeneous polynomial G, then you can just take your sector to be the entire right half plane. That would be equivalent to real stability. So real stability is basically this property when you have you replace sector by the upper half plane, but for homogeneous polynomials, all half planes are equally valid. So yeah, so for homogeneous real stable polynomials are a special case of this, but non-homogeneous ones are not. Okay. So there is a polynomial related to the Monomer-Dimer system that has this property exactly with the right half plane, and this was shown first by Heilmann and Lieb. Basically, they showed that the non-homogenized version of the Monomer-Dimer system has this property with the entire right half plane. So if you sum over all monomer sets, the weight of that monomer set times the probability of the vertices inside the monomer set ZU, this gives you a non-homogeneous polynomial. It's not, the degrees are just the size of the monomer set. This polynomial has this property that whenever you choose things from the right half plane, you don't get a zero. Okay. But it's really actually important in the spectral independence framework to have a homogeneous polynomial. You always have to make your distribution size k-sets out of a ground set of n elements. And this is not a homogeneous polynomial. So the operation I mentioned earlier for homogenizing a distribution, you can actually do it to the polynomial too. And the way it works on the polynomial is you introduce these extra set of variables. So if z1 up to zn corresponded to being inside a monomer set, z1 prime up to zn prime correspond to not being inside the monomer set. And then you homogenize using these variables. You basically, for each term, whenever there is zi, you do nothing. Whenever there is no zi, you multiply z prime I. Okay, and more concretely, that corresponds to this type of operation on the polynomial. So if you start with a sector stable polynomial and you homogenize like this, you still get a sector stable polynomial, but with a sector that's roughly half the size or half the aperture. And that's because if you now choose z1 up to z1 prime, z1 all of the zi's and zi primes from a sector that has aperture pi over 2, then their ratios would be in the right half plane, and now your polynomial won't be 0. Okay, but you do get half the sector. It's actually important. So so when you homogenize the Monomer-Dimer system, you get a polynomial with that sector stable with a sector of aperture pi over 2. And what we show then is that whenever you have a sector stable polynomial for a sector with constant aperture, then the correlation matrix of it will have L1 norms bounded by order 1. Okay, and this basically is roughly the inverse of this. All right. So I just wanted to show you like a quick sketch of this fact of why sector stability implies that the L1 norms are bounded. The proof is, somewhat standard tricks from complex analysis. It's nothing fancy. So let's say we want to show that the L1 norm of the rows of the L1 norm of the ith row of the correlation matrix is bounded by a constant, right? So you can come up with a sign matrix. So look at the ith row. Some entries of it are going to be positive. Some entries are going to be negative. And let W be basically the sign vector indicating that, right? So for negative entries, put a -1 element in W and put a +1 in when you have a positive element. Then the L1 norm would just be the inner product of W with that row, right? And you can actually think of this probabilistically as, if you think back to what the correlation matrix was, the L1 norm of the row I would just be this expectation minus this expectation, where you're taking expectation over the inner product of W and the indicator of a sample from your distribution. But here you condition on I being inside that sample, and here you don't condition at all. So what you have to show is that basically this quantity is somewhat like stable with respect to these types of conditionings in expectation. The expectation doesn't change much when you condition on the element I. Okay. All right. So now you can basically come up with a polynomial that encodes this quantity, the inner product of W times the indicator of a sample, by just taking the expectation over Z raised to this power. Okay. This power is always an integer, so you get something like a polynomial, except Z might have negative powers too, but that's not a very important issue. Okay. So this is now a univariate polynomial in just one variable Z, and you can actually obtain it from the multivariate polynomial corresponding to mu by doing this substitution. For every entry of W that was a +1, put in the variable Z plus Z to the +1. For every entry that was a -1, put in Z to the -1. So that gives you exactly the same thing. Okay. And because sectors are closed under taking inverses, if you started with a sector stable polynomial, the thing that you get at the end would still be sector stable. So you get a univariate polynomial that's sector stable. Okay. So you can even get various different things, various different univariate polynomials that are still sector stable. Basically, if you change the monomer weight of element I, you can get all of these types of mixtures where you take the distribution condition on I being a monomer, and you take the distribution condition on I not being a monomer, and you take an arbitrary mixture of these, arbitrary positive mixture of these, and that ends up also being sector stable as well, just because of the fact that you can change these weights. Basically, this is because sectors are closed under positive scalings. Okay, so all of these polynomials end up being sector stable. Okay, so because all positive mixtures of these two quantities is sector stable, this means that whenever Z is chosen from that sector, the ratio of this and this cannot be a negative real number. Otherwise, some positive combination of the two would be 0. Okay, so this means that the ratio of these two quantities for Z in the sector is always not a negative number. It avoids the negative reals. And once you have the negative reals being avoided, you can basically take a logarithm of this quantity. There is a well-defined branch of the log that on basically the complex plane minus the negative reals. If you play around with the logarithm of this quantity, you do a substitution where you replace Z by e to the Z, you get this function H. And if you follow everything through, F would basically map things that are inside the sector to basically the image of the log function, which is like a band in the complex plane like this. When you do this change of substitution, sector becomes like a narrower band. So now you have a function that maps a narrow band like this to a slightly larger band like this. Okay. Now the quantity we were after, the difference of the expected inner product when you condition and when you don't condition, basically something related to that, would actually become the derivative of this function H here at around the point Z equals 0. And basically by Schwarz's lemma, by some slight modifications of Schwarz's lemma, you can show that any basically holomorphic function that maps this band to this band and also maps basically the positive reals to the reals to the reals would have to have a bounded derivative at Z equals 0. Its derivative has to always be bounded by basically order of 1. And that's basically the whole thing. That's how this works. Okay. So there are some other distributions that satisfy sector stability, but maybe I'll skip over those. Let me just conclude here. So what we showed was that when you have a stability result, for now we can show it for sectors, you get spectral independence and therefore mixing and efficient counting or efficient sampling for your distribution. So there are a couple of questions here. One is, if you remember back in the beginning of the talk, I showed you that there is no correlation decay in general for monomer-dimer systems, because you could have this example of a long path. But this result still shows that correlations are somewhat bounded in some sense. So the question is there a different? Is our notion of distance perhaps wrong? Maybe you can come up with a different notion of distance rather than just regular graph distances, where in the path, the two endpoints would actually should be considered close to each other, not far apart from each other. So the question is, can you just change the notion of distance, and then maybe with that revised notion of distance, you would have correlation decay. So there is another famous method for approximate counting and approximate sampling that uses roots of polynomials. It's called Barvinock's interpolation method. So the question is, what are the applications of Barvinock's interpolation method that are still amenable to this type of analysis? So I know of some, but nothing that gives you new results in terms of Markov chain Monte Carlo algorithms. All right, and finally, the major open question is, what are other distributions that basically fall under this notion of spectral independence? So one concrete conjecture here is, if you take a set of 0, 1 vectors whose convex hull always has bounded edge lengths, then for that, the correlation matrix should always be bounded by basically a function of those edge lengths. Or so when the edge lengths are bounded by a constant, the correlation matrix should probably have a maximum eigenvalue bounded by a constant too. So this is in line with the conjecture of Mihai and Vazirani on basically mixing of random walks on these types of polytopes. All right, thank you for listening. Thanks so much. Yeah.
Nima, for the talk. Are there any other questions? So I don't see any new questions. So I had a couple of questions, if there are none other coming. And of course, everyone is, so you're welcome to leave. It's 11 p.m. here. So
yeah. Thanks for staying up so late.
Yeah. Okay. So what so the reason you don't need this unary weights kind of thing that Jerem Sinclair need is because you don't need the mixing time analysis at all. It only comes in the computation of the Pfaffian, and that's a fully Polynomial.
Yes,
it's a Polynomial.
exactly. Yes. So basically, the unary weights basically somehow imply that you have correlation decay in the dimers too. But here you can ignore the dimers. That's the main difference. So basically, the Glauber dynamics on monomers always mixes in all graphs, regardless of the unary weight property. But the point is you can't run the Glauber dynamics of monomers in general graphs. You can only run it when you can count perfect matches.
Yeah. Okay. And about the third point here about Barvinock's interpolation method. So it's basically when you have enough information about where the zeros are lying, and then you can get some new notion of some weakening of log concavity based on that. Is that right?
Yeah, or maybe even just this fact that the L1 norms of the rows, the correlations are bounded in the sense that L1 norms of the correlation matrix are bounded. So this has been shown. You can show this for some applications of Barvinock's method. For example, for let's say permanence of basically tensors is some result that Barbaric has, where he shows that roots cannot lie in certain regions. You can convert that to the correlations being bounded, but that doesn't give you anything new in terms of Markov chain Monte Carlo algorithms. Basically,
because the chain is not easy to implement, or something like
no, the chain is easy to implement, but people already knew that this mix. Yeah.
Okay, no questions still, so maybe I can thank Nima again, and thanks for giving the talk.
Yeah, thank you so much. Have a good day.
Thank you, sir. Thank you so much.
Thanks.
Yes. So.
Okay. Yeah. So tomorrow.
Yes, see you tomorrow. Good night, sir.
Good night.